Okay, so let's have a look at one or two more examples of things or bodies which execute simple harmonic motion. Well, first, let's remember our equation that must be satisfied for a body to perform simple harmonic motion. There it is. The force has to equal minus some constant times x. Well, it worked for that mass spring system we had, and in that case the constant just happened to be equal to the spring constant. But it doesn't have to be anything. It doesn't have to be anything to do with springs at all. Here's a good example. Supposing we had a liquid in a tube, in a U-tube. Well, so you can imagine this kind of glass U-tube, open at both ends, with some liquid. It could be water or mercury or whatever you like. Well, if I just left that to find its own level, it would obviously find an equilibrium position, and I might label that with a dotted line here. But you can imagine kind of blowing in one end, say the left end, or exerting a pressure somehow. Well, that would cause a displacement. And so let's draw that situation. So let's imagine a pressure has been exerted in the left tube there. Someone's blown in the tube or blowing in the tube just to keep the water at a different level. So it would sink down on the left, but it would also rise up on the right hand side. And therefore we've created a displacement. And you can kind of imagine, can't you, that if you then stopped blowing, took away the pressure on the left hand side, then the water would oscillate. Well, it turns out it would oscillate simply harmonically. There's a displacement here equal to x, and it can be shown that the force on the water due to the weight of the water there is actually equal to 2 times the density of the water, or whatever liquid it is, times g times the cross-section area of the tube times x. Well, you don't need to know this equation, and you certainly don't need to be able to derive it for your exam. But the reason I've given this example is just to show that, well, as long as this thing is a constant, is all that matters. Well, we can see that 2 is a constant, the density of the liquid is a constant, g is obviously a constant, and the cross-section area of the tube is constant. So because that whole thing is a constant, well, it therefore satisfies our condition for SHM. And it doesn't have to be anything to do with springs or spring constants. Well, let's look at one more example which does have something to do with springs, because it's another common example. And this is a case where you might have a spring on each side of an object kind of attached to a post. So it's quite a common example. So there's a kind of blue object there in between two posts connected with two springs, and let's suppose they're each identical with a spring constant K. Well, if we let that find its own position there, then that would give us an equilibrium position as always. But you can imagine displacing it. Let's displace it to the right. Let's displace it this way. Well, we can see that this spring is now stretched. This one is now kind of stretched less. They're both actually still in tension this time. And therefore there's a displacement of x. And well, it turns out this time that it's a bit tricky to show, and again it's probably worth looking at my link. You'll see my link in the notes on how to derive this, but it turns out that the force is equal to minus 2 times the spring constant times x. But that still obeys our fundamental simple harmonic equation, F equals minus kx, because this time it's this 2 times the spring constant, which is a constant. So still works, and we've still got SHM. So we've looked at a few examples. This equation that we've written down can be described in words as well, and it breaks down really into two conditions that need to be satisfied for a body to perform simple harmonic motion. Well, the first condition is that the force on the body is proportional to the displacement from an equilibrium, which is really saying that F has to be proportional to x. And we found that with our mass on a spring in the beginning, because it obeyed Hooke's law. But it was also true in the other two examples. Well, the second condition is that it has to be directed towards the equilibrium position, that force, and that's really the minus sign. So we have to really say that F is equal to minus. That's where we get our minus sign from. So those two conditions are actually encapsulated by that equation that we have been writing down all along. But sometimes exam questions do ask, what are the two conditions for a body to perform simple harmonic motion? And you have to write them down and explain them. I would suggest writing the equation as well. Of course, because F equals m times a, Newton's second law, well, that means that if the force is proportional to the displacement, then the acceleration must be proportional to the displacement, because force and acceleration are proportional to each other. So it's worth noting that there's a kind of alternative way of describing the conditions for a body to perform simple harmonic motion. So instead of saying the force is proportional to the displacement from an equilibrium position, you can say, well, the acceleration must be proportional to the displacement from an equilibrium position. And instead of saying the force is directed towards the equilibrium, you can say the acceleration is directed towards the equilibrium. So just an alternative, but they're effectively identical.